I'd like to ask you first how you'd like to define yourself, or maybe first time listening to you.
Yeah, sure. So I work at Brown University. I moved recently in the summer, and my group works with machine learning, applied machine learning, to design materials and structures. And on the side, sometimes we also develop algorithms in the machine learning field and other fields as well.
If we think about the problem we have especially in soft robotics or material science, sometimes when we design new materials, there's a material aspect, then there is the geometry and the structure. And there's two approaches. Either we use our intuition, and sometimes it gets very complicated, and I think that's where you try to help to come up with such a new material or structure. How do you see the two sides? If you design a new material, can you give example designing new material structure? It could be very challenging by intuition, and when maybe machine learning or optimization, which I love if you can dissect what's the difference, could fail versus our intuition as a designer.
Right. Yeah, that's a great question. So there are different ways that machine learning and optimization algorithms can help in the design process. The easiest example to consider, perhaps also the less interesting, but we'll start there, is for the cases where you already have a concept in your mind, you already have an idea, but you don't know exactly what the parameters should be for that particular concept. So let's say that you know there has been decades of development in aircraft design. So there are many components that you already have a good idea about what they should be. So what you can do then is just parameterize them and change those parameters, all of those parameters, in a controlled way, in a guided way, in such a way that you get better performance, lower fuel consumption, for example, or whatever it is. And this happens at the large scale, but it also happens at the small scale, at the microstructural level for the material. It's the same thing. As long as you can control the components or chemistry, mixing different chemicals and different compounds to come up with a particular material. So this is the case where things are more or less controlled, and the scientist is very important because an idea, the concept that you're exploring, assigns a lot of potential to the problem that you're trying to solve. Do you see what I mean? On the other side, there's a more open-ended problem called inverse design problems, where there you basically say, no, I do not want to have a preconceived idea, and I want to still find the best possible solution that solves my problem. That's a different way of putting it. There you're trying to push to the algorithm all the complexity, even to come up with a particular concept. And that second route is particularly interesting for us, and that's what we are exploring at the moment, actually. Where we're trying to have the machine learning algorithm or the optimization algorithms to actually come up with a design for a particular function instead of being the other way around.
So I think your article in iMechanica 2020, it was really an excellent article. I think it just written in a simple way, just people in material science can relate why we should use it. And I think this gap, I'm still also learning. So I want to maybe ask you one of the question I think was asked to you by one of members, that if we, for example, just for listeners to make sense of what you do, if we have like a rubber, and that's part of my work also, if we have a rubber and we have like solid inclusion in this rubber matrix, and we want to reduce the von Mises stresses as much as possible. And in your article, you spoke about the traditional technique in machine learning and advanced one, and what's the difference between optimization and machine learning. And I find there's a lot of things. I hope that you can just guide us through in a simple way for people listening, just when I should use this or this. And if we speak such a problem like that, rubber matrix and inclusion in the middle of the matrix to reduce the stresses, how you can design that in a certain way, since we have maybe play with the morphology, with the architecture of the inclusion. If we speak like one or four inclusion, I don't know, we can increase numbers here, but it seems very complicated. Maybe I'm wrong, but I'm curious from your point of view, if we have such a problem, how you can start thinking to solve this problem, for example.
Mm-hmm. Yeah, I understand. So the first part of your question about machine learning and optimization and when to to consider one or the other. As you will see in a moment, the lines are actually quite blurred nowadays between optimization and machine learning. But in a conventional way, let's say, you use machine learning when your target is to learn a model in the context of engineering. So what you're trying to do when you're using machine learning is whether you're classifying, regressing, finding clusters, even to some extent generative techniques, you are collecting data and you're making sense out of it, finding patterns and most of the time really interpolating the data in a high dimensional space. It's a non-trivial task, but it's still largely interpolated. That's one thing. And this can be very useful in engineering because oftentimes the reality is so complex, there are so many variables that you actually cannot make sense of it. You don't have a clean analytical model for every engineering problem that you have out there. If you do, and the analytical model works well, you don't need machine learning in that particular case. So that's the usual case for machine learning. Optimization is different in the sense that what you're trying to do is finding a particular solution, a particular optimum. That could be, maximizing properties or minimizing, but you're really trying to find that one solution, right? In machine learning, you're trying to learn the entire domain. In optimization, you're trying to find a particular solution. When it gets interesting is that nowadays the lines are blurred. In fact, there are optimization algorithms that actually are more powerful because they also have regression techniques from machine learning, for example. You also have very interesting generative machine learning models that are indeed trying to generate new data, even though it is a bit contentious. Most people still claim that they use so much data they are still interpolatory, really. But at least, there's a lot of push for blurring the lines and actually having optimization and machine learning working together. Because if you make sense of the world, if you have a model underlying your optimization process, then you should get closer and faster to the global optimum.
Maybe a quick question here again for the data, since you mentioned that sometimes, especially like hyperelastic materials, sometimes in the simulation we use some tools, physics engine tool, and it seems that it doesn't really capture what's happening in certain region of the behavior. And maybe question to you, when you have this experiment, and I think you touched on that, if it's really noisy, uncertain, and we need sometimes in the lab, that data is not that, not all the time reproducible, and we have the simulation. And I'm curious from your work, how you merge the two together so that you can give like understanding or complete the story behind the model of the structure or the model of the material.
Yeah, so that's another excellent point you're bringing. We know that models are not perfect, and in fact, we even know that experiments are not perfect. They can have uncertainties because, the temperature in the lab is different, or because when you're modeling, you don't have the full physics of the problem, and you can actually have an inaccurate prediction. So this is actually where probabilistic machine learning techniques, Bayesian machine learning techniques in particular, are very powerful because they're not just trying to make your prediction, they're also trying to quantify the uncertainty, what you don't know about what you're predicting. And this provides you more confidence that you are, indeed having a prediction, but you know what you don't know, or at least you estimate what you don't know. That's one. That can be very helpful. And we use probabilistic machine learning strategies quite often, to be honest, because when we are working with experimentalists, we see how valuable this kind of information is for them. But you also mentioned another thing that is very important, which is the possibility of having data that comes from different sources. So you can actually enhance the experiments, which might be expensive and time-consuming to run, but it's still, as close to the ground truth as you can get. It's the real phenomenon. But you can augment that data with simulations, for example, or any other kind of modeling strategies that you want to pursue, which might be of lower accuracy. We call it low fidelity or lower fidelity. But maybe you have more data. So then what you can do is you can put the things to do things together. In fact, you can even have more than two sources of data and actually learn from lower quality data but in large quantities, and then only probe the experiment in the right places, if you will, in the best possible places. And in fact, at Brown, I'm very fortunate to have an outstanding colleague, George Karniadakis, who has been one of the pioneers in these multi-fidelity machine learning methods. And it's really interesting, his work.
Excellent. Maybe I'll touch again about when you mentioned generative design. And maybe we can go again, for example, the matrix, and we have the one inclusion, or say multi-material design, and we have to come up with different architecture for the multi-material we have. How do you see generative model here can come up with maybe, I don't know, just new designs? And at the same side, we have this intuition, because still, maybe if you can clarify your view about the generative model, like the ratio autoencoder, for example, this kind of thing, is how we can use that for material design or soft robots, and especially if we have two different materials. And it seems complicated because there's many dimensions here, and you spoke about how we can use model order reduction so that we can focus on the interesting part, but how you can do that from the lens of intuition as a designer and the lens of generative models to come up with what other possibilities we have. And when we know that's a limit, just this is the limit.
Mm-hmm. Yeah, so as we know, there are a few things that most machine learning models are not very good at, let's say. It is oftentimes difficult to build an intuition for what algorithms are really doing, because by definition, machine learning models are models that have many parameters. In fact, most modern machine learning models are over-parameterized. They have more parameters than you have data, for example, which sounds counterintuitive, but it's shown time and time again that in many different scenarios, you can actually get great performance by just optimizing this over-parameterized space, and actually it has really interesting properties. You can even follow how the error gets lower with the fact that you have this over-parameterized space. So there's really, a counterintuitive set of results that are explaining the success of machine learning, but they're not contributing to building that intuition that engineers are so good and scientists are so good about. So I think because of this, we should not look at machine learning as a panacea, if you will, a cure for all evils. I think machine learning as it stands is a tool, a set of tools that should complement the insights and the knowledge accumulated by humanity in different scenarios, right? And if you have deep understanding, again, a physical equation that actually has meaning and clear models, they should be the starting point. And you can bring in the machine learning tools as to guide the process or to augment the process to have better accuracy, explore regions of the space that you couldn't explore because it's too fast, things like that. So that's one. It was a long answer, I'm sorry, but just to be sure about everything has their own applicability. However, there is interesting literature out there about using machine learning tools to build equations. And I know that you've interviewed Hod Lipson. Professor Hod Lipson, who is now at Columbia, was really a pioneer in doing this, using, in the beginning was genetic algorithms, then it developed into different strategies involving neural networks and so on, where you, even though are starting from an algorithm that is a little bit opaque, a little bit of a black box, because it outputs an equation that you can read, you can actually interpret the result afterwards as well. So it's not, a perfect cure, but if you do find these equations, and that's hard to do in general cases, but if you do find them, you actually may extract some intuition for the problem as well. So, it's such a vast field. There's so many tools out there that you can even use them to actually build that intuition that you wanted to have. But most cases, you better, keep working on that science and all the theory, because it's still very, very helpful.
Great. Maybe I want to ask you about your views. Maybe you have witnessed some article from soft robotics and material. It's very interdisciplinary. So if there is something you said like, well, I disagree with what have been done so far here, or do you think this is not the right way? Do you have this kind of different view or criticism? Sometimes when we view other approaches, maybe it doesn't make sense to.
Yes, I think that, and I think this is not just me. I think a lot of people feel this way because, machine learning, and if you want to go with the buzzword, artificial intelligence is so exotic and so exciting. And, the prospects of having an artificial being that has better cognitive abilities than human beings, and it's believed, I believe, that this is going to happen. I don't know when, but I firmly believe that we will be able to decode how intelligence really works, and we'll be able to actually achieve, higher cognitive abilities than we currently have at the moment as human beings. But we also know that that seems to be a bit far. It certainly is, the state of the art at the moment is based on brute force data. Even the amazing GPT-3 model that came out recently, with its incredible ability of answering questions, it almost does seem at the moments that there is a clear reasoning behind it, fails in very, very simple cases, basic reasoning scenarios. So we have done amazing work, excellent progress, but there's also a lot of hype about what happens in the literature. Now, to answer your question in the context of engineering, applied science, what we all clearly see is this allure of using machine learning for everything, right? And unfortunately at the moment, and this is normal when you're getting to start to know these tools, but unfortunately at the moment you have basically the vast majority of people using machine learning strategies for problems that would not require them. For example, in mechanics, soft robotics, and so on, there's a lot of work using machine learning for elasticity cases. Elasticity is solved. You mostly don't have any issues. You can actually have predictions that are very fast with different methods and so on. But it's very easy to generate data for elastic cases. So then it's the best way, it's the easiest entry point for you to test different machine learning algorithms. And there's nothing wrong with it, but it probably is not where machine learning should be used, right? You should be using it to solve for things that you really couldn't solve before. So that's one of the things that you see, and this is just an example, and there's many others. The other case, and this is more intricate, let's say, is that in computer science there was this trend, and it's clearly justified, about creating over-parameterized models, neural networks with many, many, many parameters, so many that you can actually find different configurations that will make you similar predictions. And as I said before, there are clear reasons for why this works so well in that scenario. But this is also creating a situation where people have a tendency to overcomplicate models and basically propose ever more complicated neural network architectures that really is quite questionable on whether or not they would be necessary. Especially in the context of engineering, where you usually don't have millions or billions of data points like most computer scientists do when you use search engines like Google, Yahoo, or whatever it is, Bing, and so on, right? So the two criticisms to conclude are using machine learning for problems that actually do not require it, or overcomplicating the actual machine learning algorithms for problems that actually would require machine learning but don't require that level of complexity. And that may lead to, poor predictions of uncertainty, or it interpolates very well, but it doesn't extrapolate well. And this is really exactly the opposite of the best scientists in the history of humanity have done. Einstein is the most famous scientist in our history, and his claim to fame was always the simplest possible model that explains the phenomenon, not the opposite. And as machine learners, sometimes we have a tendency to do the opposite.
Thanks so much. I think the answer was really clear and concise. I think you mentioned in one of the examples in iMechanic article that flying airplane from living room to kitchen. I think this is maybe similar to what you're trying to say here. And maybe let's bring another question. Why do you think we tend to do that? Since we have the material science and here the part of using machine learning optimization, what led to these two problems we have here? What do you think about it? Why?
Well, I can try to offer an explanation. I don't know if I would be right, but I think there's, unfortunately, on one side, there's the bad side and the good side. Let's start with the good side. So the good side is that, obviously, because there are cases where it was demonstrated that these over-parameterized models, very complicated architectures, really do bring better performance in the context of very, very large data. You are motivated to say, if they needed this to, train the GPT-3, why shouldn't I use this super fancy, very complicated AI algorithm, right? But again, when you're doing this and you're transporting it to a simpler problem or a problem with other characteristics, you actually may end up doing the wrong thing, right? So you may be well-intentioned, but actually, it just wasn't needed. That's the well-intentioned. Then I can't help it but think, I've been victims of this kind of thing before as well, but I can't help but think that in some circumstances, it looks fancier, right? It's just, you seem smarter. It's more interesting, more exciting. To actually go for very novel architectures, actually, I really didn't need all of this. And in fact, it's actually probably making it worse in many ways because I'm not being as predictive away from the training data as I should be. So there might be scientists nowadays have this inner conflict, right? That you have to be fancy all the time in order to make the news or, to go for higher impact journals. But we have to be careful because that might not be really the way to go, in my opinion.
So I want to go for the work you did with the spider structure. I think it was really interesting, the design of the spider web structure. And I really like the fact that maybe from biological evolution aspect, that how the spider, for example, can build this web. Sometimes it's different, maybe symmetric, and sometimes it's not symmetric, depending on the gravity. And this kind of aspect, how you do that from machine learning or optimization, if we compare the two things, when you consider this problem, what is actually the design steps when you look to the evolution, and then how we can maybe make it more better the machine learning? Can you tell us about the story behind this structure?
Yeah. So basically, that work was in collaboration with an outstanding experimental group led by Richard Norte at TU Delft. And the work was led by our postdoctoral scholar, Daniel Shin, and Andrea Cupertino did the experiment. So this was really a team effort. And this is one example of what we were discussing in the very beginning of this interview about actually coming up with a winning concept in the first place. So we, in this particular article, did not find a design out of nothing, right? Like say, okay, I want to have the highest quality factor possible. Quality factor is just a metric that tells you how good a sensor is, right? So, and then you want to have this quality factor as high as possible because you'll be able to do very precise measurements. For example, maybe in the future, gravitational waves and so on. So you want to push the quality factor as high as possible. But of course, there's an infinite amount of possibilities, an infinite amount of designs that exist out there. So in this particular case, the simulations were fairly expensive and the experiments are incredibly expensive. It's a very, very advanced manufacturing process. And Delft has a very specific set of settings that actually make this possible, and Richard is an expert in that. Long story short, you could not do 1 million simulations and thousands of experiments. You could do a few hundreds. Now there you have a bit of a conundrum because, okay, you have all these possibilities in design, but you will only have a few shots at really finding out whether the design is viable or not. So again, this is where the intuition, the knowledge that you've been accumulating over the years, especially in the case of Richard, because he's from the field, comes in and you say, okay, I cannot just have this huge search of the design space. Let's try to find some inspiration out there. So we went to nature. It turns out that some kinds of spiders, they actually sense their prey by the vibration of the spider web. And then they know where the exact location of the prey is. So, in a way, spider webs are nature's efficient force sensing. So we thought, could we actually just take that concept, parameterize the spider web, use advanced materials for optomechanics, silicon nitride or silicon carbide, shine a laser onto it, make it vibrate and measure this property. But instead of doing it in trial and error with experiments, which is what usually people do, even someone as talented as Richard is an experimentalist. That's a bit of what they did together with theory. Could we just use, in this particular case, Bayesian optimization? So it's an optimization algorithm that uses a machine learning regressor to probe the space in the, as good as possible, right? And find this design. And we were lucky to find out that after 150 iterations, we broke the world record at the time for the highest quality factor in those optomechanical sensors. And, the algorithm is not that fancy. It's a known algorithm. But because people that are at the cutting edge in experiments have a lot of other expertise, but perhaps at the moment they're not looking too much into machine learning, it's largely unexplored, right? So if you find the right algorithm for the right problem, you can get excellent performance for the problems that you're dealing with, as long as you have the right algorithm for the right problem.
Excellent. So since we're close to the end, I have a few questions for you. The first one, in your lab, what are maybe still problems do you think you would love to explore with your group? I mean, maybe it's very challenging, or maybe not touch it in depth when it comes to structure, material. You think this is not really like uncharted territory that we want to explore. Do you have any ideas, or do you think you can share some?
Yes, sure. We're exploring quite a few things, but I'll try to keep it short. One idea that we are really, honestly, very excited about, and that frankly seems very unexplored, is the notion of cooperative data-driven modeling. So what we've seen in the last few years is that people are excited about machine learning, and there's fantastic examples of good use of machine learning in design and analysis. But people are still living in bubbles. So, my lab is doing a particular model for a particular material. Someone else's lab is doing whatever model for whatever problem of interest that they have. And, the only thing that exists out there that is actually quite popular is transfer learning. So, imagine that you come up with a machine learning model for a problem. I have a different problem, but I believe that has something in common to yours. So I can take your neural network and just retrain it, right, to transfer learning, train it again, in the hope that actually you've learned already something and I'm going to just learn for the additional thing that is missing. But when I do that, there's an unfortunate consequence. Neural networks suffer from what is called catastrophic forgetting. So I learn for my problem, but I forgot how to solve yours. I would have to go back to the neural network that you trained, so now I have two models. This is not a way to cooperate. You should not destroy someone else's work to learn for yourself. There's a field that is still kind of small in machine learning called continual learning or lifelong learning that is really kind of making the first steps in trying to address this. We, in the last 3 years, quietly have been working on an algorithm to actually do cooperative data-driven modeling. And the student is Alexander Bekovic, and he basically had to develop a pruning strategy tailored for our continual learning approach. Then we basically came up with an architectural continual learning strategy of ourselves, where we cut the connections, save the sub-network associated to a particular task, and then train for the entire network again, cut all the connections and learn the next task, keeping connections that are common without touching them, but that brings the continual learning. Once you're predicting, you're going into the right subnetwork. And we apply this to ImageNet, the standard data set in computer science, and we started with 96% accuracy for 10 classes, and then we kept learning more classes, and we stayed at that accuracy. And the state of the art in that literature ended up with 76 or 70-something percent. So at the end of the 10 tasks, we were more than 20% better in terms of accuracy than the literature. And that made us very excited, because then we could apply this, for example, to material science, to materials problems. And then actually last week, we just released the paper, Cooperative Data-Driven Modeling. We're applying this to the problem that you were describing, hyperelasticity for, in fact, actually, it was to plasticity of material microstructures, which is even a little bit harder than hyperelasticity.
Excellent. Congratulations for the paper. Maybe we'll check it out.
Thank you. We're very excited about it. I think this is going to be important for our group, at least.
In the description. Maybe the last question for you. What's your aspiration, Miguel, in your work? Maybe you're clearly so passionate about what you're doing, and I feel that you're so driven about solving these problems. But what is your ultimate aspiration with your group or in the field?
I still have the dream that we as a group will contribute to somehow a small step to artificial general intelligence, where we will actually get or help getting closer to reasoning. And it's, I'm an applied scientist, and it's weird for me to say something like this, but the dream is really that, to help computer scientists in that quest. Because I also do believe that if we do that, then we'll be able to design, analyze, create new theories that are completely outside our grasp at the moment, because the design spaces are too vast, because the phenomena is too complex for our human minds to handle. I'm sure this is far away, but you asked for the dream, that's the dream.
Okay, maybe another question. Did you receive any advice, maybe stick to your mind? I don't know if there is someone give you advice or something you would like to share, maybe was a life-changing for you in the career or perspective about solving problems. Do you receive any life-changing advices?
Well, I always am careful about providing advice to others because, I tell you what, looking back and especially, observing scientists that are better than myself, I think that you as a scientist, no matter at what stage of your career you are, should never try to take the shortcuts. I don't think that publishing a lot of papers, or trying to go always for the low-hanging fruit in science is really the way to go. And if you think about it, of course, this is an obvious, it's an obvious piece of advice of observation. But in practice, it's very difficult in the world of today to actually do that, It would be much easier for Alexander, for example, to, take a transfer learning algorithm and apply it to a particular problem, right? The algorithms exist, the problems that you're trying to solve, and, there's a lot of people doing that, and there's nothing wrong with it. But what I'm trying to say is that it's incomparably harder to say, well, this algorithm doesn't exist, so could we contribute to it? And, the algorithm is not perfect. I'm sure that people will come up with much better solutions in the end and so on. But he did not take the shortcuts. He tried his best to come up with something new. And frankly, this is a lot easier to say than to do. And it takes a lot of resilience and belief in yourself to actually pursue answers, solutions for problems that you don't have the answers and the solutions in the first place. And it turns out that maybe in the end you won't find them. The world is not rosy. Maybe, you were not lucky with the problem that you defined. The problem was too hard, or perhaps you didn't have the right knowledge to get to a particular solution. And that's fine. That should not be the end of the world in science, right? We are paid to explore, to find new knowledge. Sometimes we do, and sometimes we don't. Going for the low-hanging fruit, to publish a lot, to get a job, to continue doing the same, is nonsensical. This is not what science is about. And if you are a young scientist or a senior scientist, even if you didn't hear anything else from this conversation, be true to yourself, search for true knowledge, and try to contribute honestly to make science a better place. If you are successful, you'll be tremendously successful, and you'll climb to the pinnacle of science. But if you're not, you've done it, you've tried it. It's the process, not the result. And I think we as scientists tend to forget this quite a bit, to be honest.
First of all, I would like to say thank you so much for being honest, and I really deeply respect what you say. I think that actually what we need. So, mad respect to you. Thank you, Miguel, for saying that. I don't know if you have any final words. I think you said really great words, and I don't know if you have any final words for people listening, or maybe was of robotics field. I don't know if you have any final words like to say.
I would like to thank you, and I would like to thank the work that you're doing, and the fact that you're putting yourself out there and interviewing different people from different backgrounds, and learning and teaching others about what people do. Please keep up. I'll be following your work closely, and best of luck.